Hello, today's video shows some failure symptoms and the repair of Motorola TLKR T5 and T7 radios. Of the 6 radios shown in this video, 3 had failed for the same component, a ceramic filter. The 2 radios on the left were first identified as being faulty. The initial indication of the fault was the receive symbol being permanently displayed. The 2 radios on the right seemed to be both working okay. The far left radio was dismantled in order to diagnose the faulty component, but otherwise had exactly the same failure characteristics as the radio shown second from the left. The second and more obvious failure indicator is the inability to receive any audio. However, transmission works fine. On a healthy radio, pressing the monitor button will produce a static hiss. The faulty radios acknowledge the monitor button press, but are otherwise silent. On the PCB, it's evident that these radios are in actual fact produced under license to Motorola by Uniden, a Japanese electronics manufacturer. At the heart of the radio circuit is an AN29160AA, a highly integrated radio transceiver chip manufactured by Matsushita. The device datasheet provides an example application circuit, and the application circuit depicts a dual conversion receiver, and in the lower right hand corner of the circuit diagram we can see a 450 kHz ceramic filter for the second intermediate frequency stage. After some diagnostics and research, this filter was determined to be the cause of the fault. There are numerous reports on the web of this type of ceramic filter being a common cause of failure across a wide range of two-way radio equipment and scanners. Fortunately, compatible ceramic filters are easy to obtain and the component is relatively straightforward to replace. This is certainly not the best example of how to desolder a component. For a start, I'm using leaded solder, which is not compatible with the lead-free solder used on this PCB. Notice how the solder joints instantly turn white when they cool down. To avoid contamination issues, the lead-free solder on the affected joints will need to be removed and replaced with leaded solder. The 3 solder joints on the right are all connected to the PCB ground plane. Although the solder side of the PCB incorporates a thermal relief around each of these pads, on the component side the thermal relief is missing. This makes clearing the solder from the through-plated hole more difficult on these 3 pads. By gently wiggling the pins using a pair of tweezers, it's possible to determine if a pin has been fully desoldered. The desoldered pins move easily. It only takes a tiny solder bridge within the through-plated hole to prevent the component from being removed. Fortunately, the designers of this PCB have oversized the holes for this component. That generally makes the component easier to remove. If the through-plated hole contains a bridge of solder close to the component side of the PCB, the lack of thermal relief from the ground plane on that side of the board makes it difficult to remelt the solder bridges. Often the easiest solution in this situation is to apply fresh solder and try again. It goes without saying, care must be taken to avoid disturbing the small surface mount components that are located close to the solder joints for this filter. With the last pin desoldered, the faulty ceramic filter can be removed using gravity. It's necessary at this point to remove the remnants of the lead-free solder from the pads, again taking care not to disturb the small surface mount components nearby. The large quantity of flux that can be seen on this PCB has come from the application of solder and from the desoldering braid. I very seldom use additional flux for this type of work. Here the PCB is being cleaned in preparation for the replacement filter being installed. In this case I'm using methylated spirits because it's the only thing I had to hand, but I would recommend using a proper PCB cleaning product. There are a number of reasons why methylated spirits is not suitable. I was unable to find an exact replacement ceramic filter using the manufacturer's part number printed on the device package. Furthermore, the T5 and T7 radios appear to use different part numbers. Several manufacturers produce PIN-compatible filters with similar part numbering scheme. The only area of ambiguity was over the choice of filter bandwidth. A number of choices are available, including ±2, 3 and 7.5 kHz. I decided to use a filter with the tightest bandwidth of 2 kHz in this case. I theorised that a tighter bandwidth at the IF stage might improve the radio's ability to discriminate weak signals. If testing proves otherwise, the filter can be changed later for a higher bandwidth part. I'm positioning the PCB in order to get a better viewing angle. Once again, the PCB needs to be cleaned to remove the residual flux. These ceramic filters are constructed using a three-stage stack of series and parallel elements. This is why the component has 3 pins which must be grounded. I suspect that in the case of the T7 radio failure, one or more of these series elements has become partially short-circuited, causing the filter to let through frequencies which are outside of the pass band. This theory was supported by the observation, not shown in this video, that powering the radio with the ceramic filter removed caused the continuous receive signal indication to disappear and a healthier sounding hiss of static to be heard whenever the monitor button was pressed. When the radio was powered on, the results were immediately obvious. The receive symbol is no longer permanently displayed, and the radio is able to receive signals normally again. Both of the faulty T7 radios had the same symptoms. After repairing the two faulty T7 radios, I became aware that this T5 radio had distorted audio on reception. Without any better explanation for the cause of this problem, I decided to try replacing the ceramic filter. To dismantle the T5 radios, it's worth noting the hidden screw within the loop antenna. You'll notice that the general PCB layout is remarkably similar to the T7 models. After replacing the ceramic filter, I noticed that the receive symbol was intermittently blinking on the display. However, the problem with the distorted audio had been cured. The blinking receive symbol indicates that the squelch threshold is incorrectly adjusted. This can occasionally be heard when the squelch sometimes fails to close cleanly. On the PCB there are numerous potentiometers that have been preset during manufacture. One of these potentiometers is likely to be the adjustment for the squelch threshold. Referring back to the example application circuit, it can be noted that several components are responsible for the receive signal indication to the microcontroller. Indeed, one of these components is drawn as a variable resistor. These components are connected to pin 27 of the transceiver IC, which is in the lower right hand corner of the device package. To adjust the squelch threshold, first set the CTCSS code to 0 so that any received signal audibly opens the squelch. Setting the threshold by ear is far easier than looking at the received signal indicator on the display. The position of the potentiometer RT404 can then be adjusted to set the squelch threshold such that the nuisance activation is eliminated. Out of 6 radios, 3 had the same component failure. The radios were purchased in pairs in the order they appear here. So, with half of the radios failing for the same component, I guess the question is, should I replace the ceramic filter on the other 3? I hope you found this video useful. I'll include relevant links in the video description.